Okay, now we will do question number 3. So a third order unity feedback system is shown in question 3, where GC is the system controller and G is the plant. So this is the plant, system plant, and this is the controller, K. Okay, and the open loop transfer function, this G is 1 over s plus 3, s plus 6, s plus 12. This is a type 0 system because there is no pure integrator. 1 over s raised to the power 0. This is type 0. Okay, 1 over s plus 3, 1 over s plus 6, 1 over s plus 12. There are 3 poles at minus 3, minus 6 and minus 12. So it is a stable system because the poles are in the left half plane. So initially the system operated at 25% overshoot, 25.4% overshoot with a value of gain K, with the value of gain K and natural frequency 6.57 radian per second. Okay. Determine the closed loop dominant poles of the system. Minus zeta omega n plus minus omega n under root 1 minus zeta square. We did earlier the dominant pole, closed loop pole. So here we have omega n, but we don't know zeta. So how we will get zeta? We will get zeta from the overshoot, from the formula, like in the previous questions we did this. So for the 25.4% overshoot, our zeta, we will calculate the zeta. So the zeta comes out to be 0.4. This is the zeta here, 0.4. Let me show you some formulas. Here we can see that the formula yes. So percentage overshoot, our percentage overshoot is 21. How much is it? It is 25.4. so 25.4 is something here, and it will give us like this one more than 0.4. so it comes out to be yes, he has used here 0.4 solution. Okay. Omega n is given 6.57. okay, now dominant poles will be minus zeta omega n plus minus omega n under root 1 minus zeta square. This is the formula for the dominant poles. So put these values, multiply this, you get this, and then this term, calculate this term, you will get this. This is omega d, right? 6.02 j. So this is the dominant pole of our system. And how will we get gain? We will get gain from the formula that K is equal to 1 over GS magnitude, like this, 1 over GS magnitude. So 1 over GS will be equal to S plus 3, S plus 6, S plus 12 magnitude, and put one point here, minus 2.628 plus 6.02 J. Put this one by one here and then calculate the mod. You can do this directly with the calculator. The modern calculators, like I have FX570EX, it will calculate easily the answer, and it comes out to be 463.57. so this is the gain with which the system is operating at these dominant poles. The root locus is passing through these. Okay, this is the part 1. So the second part, we come to the second part. Compute the settling time, peak time, and steady state error. Very easy, because we need to know the two quantities, zeta and omega, and from these two quantities we can determine all of these quantities. So you can see that first we will calculate the settling time, Ts, that is equal to 4 over zeta omega n. 4 over zeta omega n, this is the standard formula. Put the values here. Zeta omega n is basically this term. So 4 over 2.628 is equal to 1.522, and Tp is equal to pi over omega d. This is your omega d. So pi over 6.02 gives us 0.522 second, And steady state error, how we will calculate the steady state error? It is a type 0 system, so its steady state error will be 1 over 1 plus kp. And what is kp? Kp is simply limit s approaches to 0 into g of s. So make all s here zeros, you will get 3 into 6 into 12, okay, and then multiplied with the gain k. Because of that k, what we calculated, gain 463. So 1 over 1 plus 463.57 over 3612. So from why 3612? Because limit s approaches to 0, its formula. I tell you its formula. Yesterday we also did this. So this is, you can see the steady state formula: 1 over 1 plus limit s approaches to 0 g of s, 1 over 1 plus kp. This is the type 0. Type 0 means there is no integrator, pure integrator in the plant, so there is no 1 over s term. For for type 1 system, if n is a 1, n means s power of the s. If there is 1 over s here, one integrator, then it will be the velocity constant. So the steady state will be 1 over limit s approaches to 0 s into g of s. This is s into g of s. Here we don't have s here, but here we have s into gs, because this s will cancel the s of integrator of the g, and then we will put s 0 and we will get the term kv. Okay, so steady state error is 1 over kv. Here steady state error is 1 over 1 plus kp. So coming back, our steady state error will be 1 over, this is a type 0 system, so it will be simply 1 over 1 plus kp, 1 over 1 plus kp. This is kp, 463.5 over 3 into 6 into 12. So you calculate this with the calculator and you will get this 0.318, that is 31.8% steady state error. Okay, the third part is using the same overshoot specification. Same overshoot means, what was the overshoot? It was 25.4%. Yes, same overshoot. Design a PD controller. We did earlier the same method: theta 1, theta 2, theta 3, 3 poles. So we have the 3 thetas, add them, then subtract 180, and then calculate your theta z, and then calculate your z. So your PD will be s plus z. Okay, so this will be same overshoot means zeta is 0.4, and design a PD controller to reduce the peak time to half of its original value. Peak time, what was the peak time? It was 0.522 second, divided by 2, you will get 0.261 second. Okay, now the formula is TP is pi over omega d. So calculate your new omega d. Your omega d now will change. Your new omega d will be pi over 0.261, that will be 12.04. Now you will have a new omega n. Okay, so omega n is equal to omega d over under root 1 minus zeta square. So zeta will be the same 0.4, put it here, and you will get new omega n, which is 13.13. okay, so you will have new dominant poles. How you will get new dominant poles? Simply minus zeta omega n plus minus omega n under root 1 minus zeta square, or you can put it here minus zeta omega n, that will be the zeta omega n, plus minus that is omega d 12.04. Here comes your 12.04. so these are your new dominant poles, and your old poles were minus 3, minus 6, minus 12. Now you have to move your root locus from these new poles in order to get your desired transient response parameters. So for the PD controller, we calculate theta 1, theta 2, theta 3. Theta 1 is equal to 180 minus tan inverse 12.04 over 5.25 minus 3. Okay, you calculate this and you get this angle 100.59. For the theta 2, simply tan 180 minus tan inverse 12.04 over 5.25 minus 6. And for theta 3, 180 minus tan inverse 12.04 divided by 5.25 minus 12. So you get 60.72. Now add all of these and then subtract 180. You will get theta z. So after theta z,
Sorry, how do we get the theta?
which one theta? This one, theta 1.
Yeah, theta 1, we have the root theta 2 and 3.
Yes, the theta 1, this is the formula, standard formula for the PD controller. 180 minus tan inverse this one 12.04 imaginary part divided by 5.25 real part minus 3. Okay, this is mentioned in the design of the controller. You can see in the design controller you have to use this formula for this.
Theta 2 and 3.
Theta 2, you calculate that theta 2 with 180 minus tan inverse 12.04 divided by 5.25 minus 6. Put this 6 here, minus 6. You get theta 2, and similarly theta 3, put that 12 here. Okay, so you get theta 1, theta 2, theta 3 for the 3 poles respectively. Then add all of these angles and subtract 180. You get the theta z, your new controller, that the placement of your 0 of the PD controller. Basically you are placing your 0 of the PD controller, 67.76 theta, and then tan theta z is equal to 12.04. that is basically the trigonometric formula, 12.04 divided by z minus 5.25. so from this you will calculate the location on the real axis, that is the z, that becomes 10.175. This is your 0 placement of your PD controller. So your PD controller transfer function will be s plus 10.175. so it is at minus 10.175, this 0. Okay, and what will happen if you incorporate this PD controller in the system? You will get this overshoot, that is 25%, and your reduced half time. So this will be the benefit of your PD controller. You have controlled its transient response. Okay, PD controller. And for the steady state response improvement, you use a PI controller or a lag compensator. For the transient response, you use a PD controller or a lead compensator. Okay. Next part is the controller design can be further improved. So this is saying what I said earlier, by improving the PI controller, the transfer function of the PI, because you see that we have a steady state error here. We have some steady state error 0.318. if we want to make it 0, we have to incorporate a PI controller, because this is the property of a proportional, this is basically the property of an integral action, because it's a integrator. So if we put an integrator in the system, in the overall function, it will become a type 1 system which will give 0 steady state error. So for the PD controller we have s plus 10.175, and for the PI controller it's given as s plus 0.02 over s. Okay, so this is your PI controller, basically proportional and integral, because if you divide s, you get 1 plus 0.02 over s. Okay, so your Kp will be 1 and your Ki will be 0.02. okay, so your now then you will calculate by combining the PD designed in A and the given controller PI, form the overall transfer function of the system. So overall transfer function, just multiply this with this and multiply with the system transfer function. This is the system transfer function. So overall it will become gain into s plus 10.175 into s plus 0.02 over 5 into 1 over s plus 3 s plus 6 in s plus 12. So in order to calculate the gain k, you have to calculate it using the same method, k 1 over magnitude of the transfer function. So by taking its inverse, it will become s plus 3 s plus 6 s plus 12, and s, this one goes to upper side and these will become down, s plus 0.02 and s plus 10.175. so you can put s here. Which s? Put this s, your desired location, this s, 1 point here, put this 1 point here, and then you will get your gain, which comes out to be 156.89. so your overall transfer function will be 156.89 into s plus 10.175 s plus 0.02 over s multiplied by the system. This is your PID, basically a PID transfer function. So just multiply these s square 0.02 s, then 10.175 s plus this, multiply this, add the s terms, and then multiply by this, and then divide by s. So you will get this term 31.93 over s plus 1599.5. So this is a PID controller. This is the P term, proportional, plus integral. This is the integral term. 1 over s is, this is 1 over s means integration, and multiplication with s means derivative. So this is your KD, KP, KI, and KD. So your KP will be 1599.5, your KI will be 31.93, and your KD, it will be 156.89. And this is your overall transfer function, which I said earlier, 156.84 s plus 10.175 s plus 0.02 over s into s plus 3 s plus 6 s. But this is your overall transfer function. Okay, so determine the values of Kp, Ki, and Kd of the PID controller, which is calculated here. Second part is prove that the design will yield a zero steady state error. Yes, it will yield a zero steady state error for the step input. For the step input, let me show you a brief formula for the types of the system. So this is basically, we see that position constant Kp, and this is your Kv, and this is your acceleration constant, and this is a table from the Norman nice book. I hope it's clear. It's still a bit blurred. The type 0 system, type 1, and type 2. So with this controller, our system has become a type 1. So type 1 system will give 0 steady state error at step input. Okay, so because our Kp is for the type 1, our Kp is infinity and our error is 0, right? So as the system type is 1, the steady state error is 0, because this is for the step input. So Kv here will be infinity, and ESS is 1 over Kv is equal to 0. Why it's becoming infinity? It's becoming infinity because of this s approaches to 0, because of this term, because your this becomes infinity. This becomes infinity if you do this here. If you do this here, because ss will cancel, and you put all of these as 0, so you will get here Kv your infinity, and 1 over 0 is basically infinity. That's why 1 over 0 is infinity, and 1 over infinity is 0. So your steady state error comes out to be 0. So this is the basically main point. Your system has become type 1. So for the type 1, for type 1 system, for step input, we have 0 steady state error. Okay. The third part is sketch the root locus and output response of uncompensated and compensated. So uncompensated, for the uncompensated, just this is your uncompensated. You have 3 poles, -3, -6, -12. So this is your these are your asymptotes, and this one goes to the infinity to terminate at the infinite, to terminate at 0 is placed at infinity. But for the compensated system, this is our compensated system. We have now 4 poles at 0, -3, -6, -12, and 2 zeros, -10.175 and -0.02. So this is our compensated system. So this pole will be terminated here. Okay, the root locus on the left of the odd number 1. Yes, there is 2. There should not be any root number 3. Yes, there is a root locus here, and this goes like this, and then 1, 2, 3, 4, 5. Yes, there is root locus here 5. Okay, 5 root locus. There is 0. There is 0, -10, and this is -12. This pole will be terminated at this 0, So this is the compensated root locus, and the time response, it will be like this. The previous one system with the some steady state error and the peak time and rise time, and now the improved system, this is your improved system with the zero steady state error, right, and improved peak time, settling time. Okay, so this concludes our question number our 3, question number 3.